Welcome to Ask and Learn.
So in this problem, we have a roller coaster, and we want to find three different things. We want to find the initial height that the hill has to be so that the car on the roller coaster can go through both loops. Call that HA. We want to find the normal force that the car experiences at point B, so we call that FNB. And also the normal force at point C, call that FNC. And we're told that initially the car starts at rest. So to first find the height HA, we can break it down to just focusing on points A to B. So from points A to B, we're dealing with height. So that means that there's a potential energy, and the cart, as it's going down, will have some sort of velocity, so it has a kinetic energy. So since there's a potential and a kinetic energy, we can use the conservation of energy. And again, we're looking at from point A, the top of the hill, to B. And this is initial kinetic energy at A plus potential at A is equal to the kinetic energy at point B plus potential at B. Since the cart starts at rest, the kinetic energy at point A will be 0. So then we can expand this, and we have potential energy mg HA equals kinetic energy at B, 1/2 m BB squared plus potential energy at B, mg HB. So we're looking for HA, and we need to find the velocity at point B. So if we think about the forces involved at B, we know that once it leaves point B, the only force acting on it is the weight, and that equals the mass times the centripetal acceleration. So at this point, that means that the normal force at B is 0. So if we expand this, we have the weight, mass times gravity, equals the mass times centripetal acceleration, which is v squared, and this is the velocity at B, divided by the radius of curvature at B. We see that the masses cancel. So solving for VB, we got gravity, 9.8, times the radius of curvature, which is half of the height, so half of 15, 7.5, and all of its square root to get rid of the square. So we have VB, the velocity at point B, to be 8.5 meters per second. So now we can plug this back into our energy equations to find the height. So plug in what we know that mass times gravity, so the mass 700 kilograms times gravity 9.8, you have 6860 times the height HA, which is what we're looking for, equals 1/2 m, so half of 700, so you have 350 times, well, VB we already found, which is 8.5. Squared plus, and then again, mass times gravity, 6860 times the height HB, and we know that because it's given to us as 15. So we can clean this up a bit. So we have HA equals to, and then all on the right is added up together. So we have 128,187.5 divided by the 6860. So we have the height at point A is 18.7 meters. So 2 down, 1 to go. So now we want to find a normal force at point Z. So again, now we can just be looking at the forces from just point B to point C. So here we have the weight of the cart plus the normal force it experiences at C equals the mass times acceleration. Here it's centripetal acceleration, so you have v squared, and this is the velocity at C divided by the radius of curvature at C. So solve for the normal force. So we have FNC is equal to, well, weight is mass times gravity. So you have m bc squared divided by rho c, then minus the weight, mass times gravity. We call that equation 1. So now we're looking for the velocity at C. So then again, we can use conservation of energy, looking from point B to point C. So you have the kinetic energy at B, 1/2 mv b squared, we know those values, plus the potential at B, mg hb, equals the kinetic energy at C, 1/2 mv c squared, that's what we're looking for, plus the potential at C, mg hc. So now plug in our numbers. We have half of the mass, 350, times VB, which we know, 8.5 squared, plus the mass, 700, times 9.8, times the height, 15, equals the stuff on the right. So we have half of the mass, 350, times VC squared, plus mass times gravity, 6860, which is just the weight times the height at C, which is given as 10. So when we plug everything in and solve for the velocity at C, we get VC equals 13.1 meters per second. Now we can plug this back into our force equation to find the normal force. So the normal force at C equals, so now plugging everything in, the mass 700 times the velocity at C, 13.1 squared, divided by radius of curvature, which is 5, so half the height, minus the weight, mass times gravity, 6860. So finally, the normal force at C, FNC, equals 17.16 kilonewtons.